Good morning, students. Today we are starting Unit 1 of the subject Measurement and Instrumentation, WE 3403, Aviation 2021. This subject plays a very important role in engineering because any physical quantity like voltage, current, temperature, pressure, or speed cannot be used directly unless it is measured accurately. Measurement is the process of comparing an unknown quantity with a known standard. Instrumentation is the science of designing and using instruments for measurement. So in this unit, we will study what an instrument is, how it is classified, how measurement systems are formed, and what characteristics they must process. Instruments are mainly classified into two types, absolute instruments and secondary instruments. Absolute instruments give the value of the quantity directly in terms of physical constants of the instrument. They do not require calibration with another instrument. However, they are usually bulky and not convenient for routine use. Secondary instruments are those which give readings only after calibration with an absolute instrument. Most instruments we use in laboratories and industries such as voltmeters, ammeters, and wattmeters belong to this category. So practically, secondary instruments are more commonly used while absolute instruments are used mainly as standards. Instruments can also be classified as deflection type and null type instruments. In deflection type instruments, the value of the quantity is indicated by the deflection of the pointer over a calibrated scale. For example, in an analog ammeter, the pointer moves according to the current flowing. In null type instruments, the unknown quantity is compared with the known value and adjusted until the deflection becomes zero. At this condition, the unknown quantity is equal to the known value. An example is the Wheatstone bridge used for resistance measurement. Null type instruments are more accurate but slower, whereas deflection type instruments are faster but slightly less accurate. Every instrument or measurement system performs three basic functions. First is the indicating function, where the instrument simply shows the value of the measured quantity, like a voltmeter displaying voltage. Second is the recording function, where the instrument records the variation of the quantity with time, such as a temperature recorder in industries. Third is the controlling function, where the measured quantity is used to control a system automatically. For example, speed control of a motor or temperature control of a furnace. Applications measurement systems are widely used in engineering applications. One application is monitoring processes, where instruments like ammeter, voltmeters, and energy meters are used to continuously observe system conditions. Another application is control of processes and operations, which is very important in automation systems. The third application is experimental engineering analysis, where theoretical results are verified using experimental data obtained through measurements. In automatic control systems, measurement plays a central role. The actual value of the quantity is measured and compared with the desired value. If there is any difference, corrective action is taken. For example, in temperature control of an oven, the actual temperature is sensed using a sensor and compared with the set temperature, and heating is adjusted accordingly. There are two types of instrumentation systems, intelligent and dumb instrumentation. In intelligent instrument, the measured data is processed and refined before display. It may include microprocessors and digital processing. In dumb instrumentation, the instrument only displays the data and the observer must interpret it manually. Traditional analog meters are examples of dumb instrumentation. A generalized measurement system consists of a series of functional elements that convert the measured quantity into a readable output. The three main elements are primary sensing element, variable conversion element, and a data presentation element. The primary sensing element is the first element that comes in contact with the quantity to be measured. For example, in temperature measurement, a thermocouple or RTD acts as the primary sensing element. In pressure measurement, a diaphragm is the sensing element. It directly senses the physical quantity and it produces an output related to it. The output of the primary sensing element may not be suitable for display. Hence, it is converted into a more convenient form using a variable conversion element. For example, mechanical displacement may be converted into an electrical signal using a transducer. This conversion preserves the information content of the original signal. This element presents the final output in a form understandable by human. It may be an analog pointer, digital display, short recorder, or computer screen. It enables the user to observe, analyze, and control the system. When the measured quantity is constant or slowly varying, the performance of the instrument is described by its static characteristics. These include accuracy, precision, sensitivity, resolution, error, range, span, split, dead zone, and threshold. The accuracy is how close the reading is to the true value. Precision is the degree of repeatability of reading. Sensitivity is the change in output per unit change in input. Resolution is the smallest detectable change. Error is the deviation from true value. Range is minimum and maximum measurable values. And the span is the difference between the upper and lower limits. Drift is the gradual change in reading with the time. Dead zone is the region where no output is produced. And last one, threshold is the minimum input required to produce output. Next, we will see the dynamic characteristics. When the measured quantity changes rapidly with time, static characteristics are not sufficient. We consider dynamic characteristics such as speed of response, fidelity, measuring lag, and dynamic error. The speed of response refers to how quickly the system responds to changes in input. Fidelity is the ability of the system to reproduce the input signal without distortion or loss of information. Dynamic error is the difference between the true value of a time varying quantity and the value indicated by the instrument. It occurs because the instrument cannot respond instantaneously to changes. Measuring lag is the delay in response of the instrument. In retardation type, the response starts immediately but gradually. In time delay type, the response starts only after a certain time. The errors in measurement are classified into cross errors, systematic errors, and residual or random errors. The cross errors are caused by human mistakes such as wrong reading, wrong recording, and wrong calculation. These errors can be avoided by careful observation and repeated measurements. Systematic errors are consistent and repeatable errors. Instrumental errors arise due to defects or misuse of instruments. Instrumental errors arise due to temperature, humidity, dust, and magnetic fields. Observational errors arise mainly due to parallax. Residual or random errors are caused by small, unpredictable factors. These errors vary from reading to reading and they cannot be completely eliminated. Calibration is the process of comparing an instrument with a standard of known accuracy. It helps in detecting errors and improving reliability. A standard is a physical representation of a unit of measurement, such as a standard resistor or standard cell. Standards are classified as the international, primary, secondary, and working standards based on their accuracy and usage. Thus, this unit explains the basic concept of instruments, measurement systems, characteristics, error, calibration, and standards. These concepts are fundamental for all electrical and electronic measurements. Thank you.